All right, taking a look at a reaction with mercury, an alkene reaction with mercury. You are going to form a three-membered ring, syn addition. Your first step, your pi bond is your nucleophile. Attacks the mercury, breaks the mercury OAC bond. At the same time, the lone pair of the mercury comes back down and reacts there. So 3 arrows, 1 step. You're going to make that three-membered ring with mercury, mercurium ion. I'm just going to draw one version of this. So OAC, plus charge on the mercury. All right, this is an H. So if I go back here and number my carbons, carbon 1 and carbon 2. This is carbon 1. There's carbon 2. So carbon 1 had the methyl on it. Right there, so that's there. You also draw the other version of this, the other, right, where the mercury not came from the top, but it also could come from the bottom. So there's the other kind of enantiomer, isomer of this intermediate. Need to make sure I balance my charge. So I have a plus charge on mercury, right? Mercury had 2 bonds to start with. Now it has 3, so it has a plus charge, right? Donated that lone pair. But I also lost the OAC, the O-acetate. It's the same thing right there. That helps me balance my charge, right? I started with a net neutral charge. I'm gonna have a net neutral charge at the end. Yep, this is the structure of OAC. This is this acetate. O is there, and the AC is this acetate part. All right, so do that. Make that three-membered ring. You always remember you make those three-membered rings so that this is a syn addition. But then the thing that comes next is going to be a trans addition, right? Because it's going to be like an SN2 reaction. And SN2, you go for sigma star, which is of course 180 degrees away. Now we have a choice though: carbon 1 or carbon 2. Which one are we gonna attack? Carbon 1 or carbon 2?
You attack carbon 1.
Attack carbon 1. And the reason why is it's more stabilized by hyperconjugation. It's more substituted, that's a fact. But the principle why it's more delta plus is because of hyperconjugation. And what's the nucleophile gonna be? It's gonna be water, right? This slash means water is the solvent. It always attacks the most substituted one. Yep, and the reason why though is because of hyperconjugation, right? It's not because it's more substituted, right? The reason it's stabilized is because of hyperconjugation.
Is that true for all like the bridged reactions?
All these three-membered rings is all the same idea, same principle, right? So you go for the anti, right? Anti-attack, anti-addition. HG, OAC, got its lone paired back. Gotta make sure you balance our charge. Now there's a plus charge on the oxygen. You still have the OAC minus floating around. Next step, you can either have the hydrogen just fall off, or you could use the OAC to grab it, or a water to grab it, right? H plus is the same as H2O plus, and OAC with an H is acetic acid, right? So either way we get there. So what does that give us after this first set of steps? That gives us HG, OAC, and it's trans to an alcohol. All right, remember my carbons again. This was 1, that was 2, this is 1, that's 2. And we made what? We made H plus, OAC minus, or you can put them together as acetic acid. So that finishes step 1. To get the mercury off, you're not responsible for knowing this mechanism. And the mercury had so little impair. The second step is this. Oh, sorry, it's NaBH4. I think I wrote the wrong thing up here. BH4. Sorry. And that just replaces the mercury with a hydrogen. Stereochemistry stay the same. The mercury is still trans to the OH. You're just replacing it with a hydrogen. Carbon 1, carbon 2. This gives you that not anti-Markovnikov. It gives you the Markovnikov. Right? The group you're adding, the alcohol, the more important group, ends up on the more substituted carbon. And it's also a trans product. Do all Markovnikov products have to be trans? No. This one is. So the two things you added, the H and the OH, end up trans together. That's what trans means. Markovnikov refers to the more important group you added, not hydrogen, ends up the more substituted carbon. And you'd also, of course, make, right? Is this having an enantiomer though? So be careful. Does this have an enantiomer? Sometimes it helps, right? So do we have an asymmetric center? We do not, right? So this is different. OH is different. Methyl is different. But then as you go, right? If you looked at it flat, you would see right, that's not an asymmetric center. Right? This is not an asymmetric center because these two carbons here are the same, and these two are the same as well. This one and this one. So it's not an asymmetric center. So you wouldn't say plus enantiomer here. That would be wrong. So let's review what happens when a mercury adds to an alkyne. So I've kind of started this in the middle of the mechanism. So the mercury had already added to the alkyne. It made a 3-membered ring with mercury. Water was the solvent. Water attacks. You see this trans product right away. Mercury's +1. Oxygen's plus 1, 2. So we start out with a +2 charge to start the mercury. The mechanism started with a mercury that looks like this. 2+. This is right from that third workshop. This was our starting reagent. And I can go back if I need to start with how we got here. But now, right, if we balance our charge, +1 gets the +2. So what happens from here to here is actually a tautomerization, right? So if you notice this carbon, if I number my carbons, 1, 2, 1, 2. Carbon 1 here has no hydrogens bonded to it. Carbon 1 here does, right? Even if it's not drawn in, that hydrogen's there, right? The hydrogen's there. Where did that hydrogen come from? It came from right here. When that bond break, those two electrons came there to form that new pi bond. And that gets us to here. That's that tautomerization. Now we're stuck with this weird, well, mercury's still on here. And we know at the end of the day, we want mercury off of this thing. Don't forget, mercury is a metal. Oxygen is more electronegative. Mercury is going to say, forget it. Take the electrons. Right? New there. Electrons go there. Form a new pi bond between carbon 1 and 2. And we make Hg2+ again. And we're ready to go for another, it's like a catalyst if we use it again. Okay? To balance our charge. Again, we had +1. Now we have +2. Balance our charge. So this gets to that enol, right? That enol. Now, in the second step, usually this says step 2, or maybe there's H+ around. The second step, we're going to take an enol and tautomerize again, but this time we're going to use an acid catalyst. Right, this was an intramolecular one. This time we're going to use an acid catalyst. Right, so this is a catalyst, which means we're going to regenerate it in the mechanism. You can do this all in one step. The pi bond can go for the H plus. At the same time, the electrons between that O and H form a new pi bond between carbon 2 and the oxygen. And you'll also notice if I circle this, where does that H end up? What does it end up as? It ends up as H plus. Because it lost, right? It's the one that lost the electrons. This H ends up here with the other H from before on carbon 1. Right? And now, right? So now it's the catalyst. So when you say catalyst, it doesn't mean it has to be this H that's regenerated. It has to be a H plus that's regenerated. Right? So there you regenerate your catalyst. Now you're done. So just taking a step back, so where did, I kind of started with this enol tautomerization, this intermediate. Where did this all come from? It came from something like this, right? A four-membered, a four-carbon piece alkyne. It's going to react with mercury, very similar to how it reacts with alkenes. Pi bond attacks the mercury. Lone pair of the mercury comes back down. We get that three-membered ring. Hg still has a 2 plus. It's that syn addition. Carbon 2, carbon 1. There's water in the system. And interesting enough, does it matter if it attacks carbon 1 or carbon 2 here? Are they any different? They're actually the same, right? So the starting alkyne was internal, the starting internal alkyne was symmetrical. So it doesn't matter. The way I have it drawn up here, it went for 2, so let's just go for 2. Notice, again, if you have a three-membered ring, what kind of products are you going to end up getting? Trans, right? They're going to come trans because it's like an SN2 reaction. Where's sigma star? 180 degrees away. Hg is now 1 plus because it got, see how it got electrons? And the water that adds has to be trans, and it has a plus charge to balance it, right? We start out with 2 plus, plus 1, still 2 plus, and this is the same as intermediate as we have up here. All right, so now here we have a halogen, 2 halogens have been added to an alkane. We have NaNH2, all right? So we have dihalogen, we have NaNH2, which is a strong base. And the way to draw it is Na plus, NH2 minus. There's 2 equivalences of it. So we're talking a lot about alkynes and alkenes. So you guys actually know how to make alkynes and alkenes. Those are elimination reactions. So you know 2 types of elimination reactions. One's an E1, one's an E2. This is not going to be an E1 because you have a really reactive base or nucleophile, right? If some with a negative charge. E1 mechanisms involve a carbocation. You're not going to make a carbocation with something with a negative charge. Never going to happen. So that means it's going to have to be an E2 reaction. So for an E2 reaction, what do we need to look for to do an E2 reaction? For E2 reaction, what do we look for? We look for beta sp3 hybridized CHs. Right? So if we consider this the alpha carbon, the one that's attached to the bromines, this is alpha, these 2 are beta. Are these 2 carbons the same? They are the same. So let's just pick one. We'll draw in some beta hydrogens. So it doesn't matter which one I pick. Do that E2 mechanism. Get things anti-periplanar. In this case, it doesn't really matter because there's a bunch of H's, they're all the same. It's going to make that first equivalent. It's going to do what? It's going to make a pi bond. A second equivalent is going to keep reacting. Draw my H's in. Which H should we go for? The H that's syn or the cis or trans to the bromine? Trans, right? E2, we want things anti-periplanar. We always go for the trans. So the final product then, oops, I added a carbon. Don't add a carbon. is that. A terminal alkyne.
Well, could you just have an H on that and it would be the same?
Right, so this would be, yeah, so I could, right, or I could flip it around and have that way too. If I had another equivalent of this, I would deprotonate the terminal alkyne and make this into a nucleophile, that carbon into a nucleophile. That's the one way we know how to add carbons.